Hello everyone. Boy, oh boy, you've been doing such good work. Mrs. Hanson here again, and we're picking up our lessons with section 5.3, learning about the patterns of chemical change. So I'm really looking at the top of page 4, just so you see where we're at in our notepad page. Types of chemical reactions. We will learn that there are 5, majority of chemical reactions fall into 5 general categories. Our text uses 6, and I'm going to cut that back to 5. Here's why. A combination, I would want you to know, decomposition, single replacement, double replacement, a larger umbrella I'm going to pull out called redox, and then an acid-base reaction which comes up in chapter 9. We'll kind of seed it today in this lesson and come back to it and visit in chapter 9. So for your lessons, I would like to write down 5 general patterns of chemical change. We're going to go through these one pattern at a time. The first of the 5 I want you to write down is called a combination reaction. Some texts call it a synthesis. We're going to call it a combination. Notice the pattern of change says I take a reactant called A and I combine it with the reactant called B and I form a single product AB. This single product makes this combination unique. From all of the other patterns of chemical change, combinations are the only pattern that makes just one thing on the right side of the arrow, a combination reaction. Notice we have an element A represented by a blue molecular atom, B represented in green, and I combine to make AB, and keeping the equation balanced, we can see that I have 4 atoms of A reacting with 4 atoms of B, giving us 4 compound AB. It is a balanced equation. We know it would need to be in the reduced form to be properly written. The opposite of a decomposition, the opposite of a combination is a decomposition, where we have compound AB breaking down into the elements A plus B. Decomposition is the only pattern that begins with a single reactant. AB breaks down into A plus B, a decomposition. Notice that these two are opposites of one another. To combine is a building process. To decompose breaks it back apart. Combination and decomposition. The third pattern is known as a single replacement. This is where we take an element and react it with a compound to produce a new element and a new compound. An element plus a compound where we form a new element and a new compound. Notice what happens here is that element A kicks out element B from the compound and steals its partner. A single exchange, a single displacement, single replacement, where the elements A and B swap places. And the fourth general category is known as a double replacement. And the double replacement, we have compound A plus B reacting with compound C, D, and we see those swap places. The 2 positive ions exchange places, forming a new compound, AD, and a new compound, CB. And remember how we always write positives first? So A goes to D, C goes to B. A compound reacting with a new compound, forming 2 new compounds. The 2 positives exchanged partners. Compound AB react with compound AD, A then combined with the compound D, and C combined with B to form 2 new compounds, a double replacement. And the combustion pattern, we said, well, this is where we take a hydrocarbon, combine it with oxygen, and form carbon dioxide and water. And it releases all kinds of heat and energy and light This hydrocarbon is some sort of fuel that you're burning in a combustion pattern. The 5 general equations, general patterns of chemical change. Combinations produce a single product. A decomposition breaks it back down. We have a single replacement where an element reacts with a compound, and a double replacement where 2 compounds exchange partners. And the combustion, where we have a hydrocarbon fuel burning an oxygen to release carbon dioxide and water. Can you practice recognizing what a combination and what a decomposition is? Pause the video and just try out labeling. Are these combinations or are they decompositions? Are you ready to check? Okay, I hope you paused. In letter A, what I want to see is if the one substance is on the reactant side or is it on the product side. I can see that the one product on the right-hand side made this a combination pattern, that copper and sulfur combined to make a single product. What makes the decomposition unique is that you start with a single reactant. And when that happens, you break down into a simpler substance. And that's our trick for picking out a decomposition, is it has a single reactant. Letter C, I notice that I have a single product. And that means that this is known as a combination. Oops, I needed a pen. What about letter D? Combination. Now letter D, this is a hydrocarbon, but it's not the pattern of combustion because there's no oxygen on the left-hand side. We need a hydrocarbon plus oxygen releasing carbon dioxide and water. But I do want you to notice that it has just a single reactant. And when it has just a single reactant, it's known as a decomposition. So we had combo, decomp, combo, decomp. Here's a nice visual to remind us about single replacements and double replacements. Single replacements. Here I have a single replacement. This girl leaves her guy for Joe. So here's Joe. And this is Mary. And this is Frank. Frank and Mary are a couple. But here comes Joe. You notice what Joe did? He displaced Frank. Frank, poor Frank, it says. A single displacement reaction. Now, here's where our Frank and Mary. And over here now is Josh and Sue. Joe, oh, they've labeled these guys all differently. Let me get this caught up. This is Joe, this is Mary, this is Josh, and this is Sue. All right, so now look what happens. Joe and Sue are now together, and Josh and Mary are now together. This is what we call a double exchange, double replacement, double displacement. The 2 positive ions simply exchange partners, a double replacement. Now with that cartoon in mind, let's classify these as singles or as doubles. Pause the video and label single or double replacement. Come back when you're ready to check. Please don't cheat yourself of the practice. Okay, so we're given balanced equation or just trying to recognize the pattern. So when I'm looking at element, let's just make them all different colors. Notice that that has 4 different characters. This is like saying compound AB reacts with compound CD. A went with D, C went with B. And so notice our color code, copper is now with chloride. They have a new last name. Hydrogen is now with oxygen. They have a new last name. This is a double replacement. Two compounds have exchanged positive ions. Now the difference here, when I recognize the elements, I have a zinc, a hydrogen, and a chloride. I have an element plus a compound. Well, I can see the zinc and the chloride now hook, and what's left is the hydrogen by itself. Notice I only have three colors, if you will, in my equation. Zinc kicked out the hydrogen, so that was a single replacement. Again, how many different elements allows us to predict? Letter A, here's a magnesium reacting with a nickel and the last name nitrate. 3 characters. The nickel is now by itself. The magnesium is now hooked to the nitrate. We have 3 different ingredients. Magnesium displaced the nickel in a single replacement. In your next, you notice that there's 4 characters: a potassium, an iodide, a tin, and a nitrate. Those are the 4 characters involved in this reaction. So 4 characters means the 2 positives have simply exchanged places. Potassium went with nitrate, tin went with iodide. That is a double replacement. Identify the characters. There's potassium. It's hooked to cyanide. Here's a hydrogen. Here is a chloride. The 4 different characters in letter C. We can see that the potassium hooked to chloride, hydrogen went to cyanide in a double replacement. And the last one to check, we had a sodium, we had a aluminum, and then a sulfate, SO4, a sulfate. That's 3 different characters. The sodium displaced the aluminum and stole its last name, the sulfate. So this is a single replacement. Now, what if they're all mixed together? Can you try this one out? Work ahead of me and come back. Tell me if they're combo, decomp, single, or double. All right. So here we're just looking to see what the pattern of chemical change is. Letter A, I have a single reactant. A single reactant means just one thing on the left-hand side. When that happens, you know to classify that as a decomposition. Now, in letter B, it looks like I have 3 characters. I have a magnesium, I have a zinc, and I have a chloride. 3 different characters means an element plus a compound. Magnesium displaced the zinc, so now it's by itself. Magnesium stole the last name, magnesium chloride. Single replacement. Letter C, what did you find? Well, I find that I have just one and only one product. And that makes that unique to a combination reaction. And finally, you would notice the K, the NO3, the H, and the Br as 4 different characters. The potassium went to the bromide, the hydrogen went to the nitrate, and you called that a double replacement reaction. Recognizing the patterns of change. Now we have a little more of a challenge here, is kind of figuring out what's missing in these balanced equations. All right, so we're told the pattern. We have to be detectives and figure out what's missing in the box. A combination reaction combines to make a single product. When carbon and oxygen combine to make a molecule, it will form carbon dioxide, a combination that simply comes out as a balanced equation already. Now, letter B is a decomp, MgCO3. When it decomposes, I've accounted for the magnesium and one of the 3 oxygens. What's missing? Well, and I ask myself, what's missing? I have a carbon and 2 oxygens that are missing. That's carbon dioxide. So it's like a subtraction problem. Think of this as an addition problem, and think of this as a subtraction problem. MgCO3, when I take out MgO, what's missing? Well, that's a carbon and 2 of the oxygens. That's carbon dioxide. When I'm adding carbon to oxygen, put them together, it's an addition problem. Decomps are subtraction problems. How about a single replacement? All right, so let's figure. I've got silver and then something. And on this side, I have lithium and silver carbonate. Now, silver is a +1, carbonate's a -2. That's why we crisscrossed and got Ag2CO3. Well, what's missing over here? I have to have the element lithium because it's now by itself, and its original last name was carbonate. The name of the compound is lithium carbonate. And remember, when I write formulas, I have to consider charges. So remember, we got to bring that around and down. Li2CO3. And the pattern of change would simply show silver kicking out lithium and stealing its last name. Silver carbonate forms and the element lithium. One more, a double replacement. We're given sodium carbonate. Now sodium is a +1, carbonate a -2. Use your polyatomic chart. If you still don't have those memorized, your carbonate, CO3 -2. And it's going to have barium, bromide, BaBr2. Now the double replacement says the sodium goes to bromide, barium goes to carbonate. When you write your formulas, remember to consider charges. When you are hooking to a new negative or a new positive, you have to balance that electrically. So the first, when sodium, who comes as a +1, combines with a bromide, who comes with a Br, it's just simply NaBr. You do not bring the subscripts with. But I find the new subscripts based on the charge. Barium, who comes as a +2, will combine with carbonate, who comes as a -2, so that's also electrically balanced. We'll need a coefficient in front of here to balance the number of NAs and BRs. So to finish that, you ended up having 2 units of sodium bromide and 1 unit of barium carbonate. And that created a balanced chemical equation. A double replacement. Exchange the 2 positive ions and check the charges as you do so. You've got an opportunity to practice. Classify, 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 and then down here you're going to fill out the remaining boxes. You have a job to do. I'll give you some time to do it. Pause the video, work ahead of me, solve each of these, and come back only when you have an answer to check. Working on page 5. All right, you must be back, so you've got these answered. You've paused and are ready to check. We have a single reactant in letter A. That's our clue that this is a decomposition. We broke it down to a simpler product. They're even showing you the bond that broke. In letter B, we can see an element, fluorine. We can see a compound, sodium bromide. And when I see that pattern of chemical change, the fluorine displaced the bromine and stole its partner. An element kicked out another element to form a new compound. So a single replacement. Letter C, what I notice is only one product. And that's our clue that that was a combination reaction. And how about this guy, letter D? We have 4 different characters. Did you notice? A hydrogen. We have nitrate. We have a potassium. And we have an OH. Remember, this is my trick. I really like you to just think about HOH for water, because now I can clearly see that I have a hydrogen and I still have a hydroxide as separate. So 4 different characters. The hydrogen went to hydroxide, the K went to NO3. This hydroxide is 1 unit, 1 polyatomic ion. So that was your double replacement. 44, do you see aluminum kicking out the hydrogen and stealing its partner, aluminum chloride and hydrogen gas? Do you notice in B how we had just 1 reactant, making that your decomposition? Hydrogen went to hydroxide, sodium went to sulfate. There's your double replacement. Think of water as HOH, hydrogen hydroxide. And here, with our next example, whoops, I touched something. This has a single product. That's what we noticed as our combination pattern. Let's fill in what's needed. In a combination reaction, the compound that formed was sodium chloride, and you can see based on charge why sodium and chloride are combined in a 1-to-1 ratio. Na is a +1, chloride is a -1. And yet the elemental form of chlorine comes as a diatomic molecule. I can't just write Cl in that box because chlorine doesn't work that way. It comes as a diatomic. So then you had to balance as well. 2 NAs plus Cl2 made 2 NaCls. Excellent. Decomposition. Well, that one compound is going to decompose into its elements. The elemental form of nitrogen is N2. The elemental form of iodine is I2. Horses need oats for clear brown eyes. Those both are diatomics. So now we'll need to balance. We'll balance with a 2 in front of Ni, 3. That gets the N's working. Oh, and then I'll need a 3 in front of the I2's. That gets me 6 on both sides. Elemental form of chlorine with potassium iodide. Chlorine displaces the iodine. Iodine, remember, is one of the lucky 7, I2. Positive ions are written first, negative ions written last. KCl. Based on charge, you know that that is a K plus, a Cl negative. So that only goes as a 1-to-1 ratio to balance charges. And now we can balance by making 2's in front of each compound. 1 chlorine plus 2 units of Ki form 1 iodine and 2 units of KCl. And a double replacement, potassium hydroxide plus hydrogen iodide. K goes to I, H goes to OH. So the first product would be potassium iodide, and H goes to OH. You can write water as HOH. And know if you were typing that in to your homework site, that would go in as H2O. But I like to balance the equation HOH. All right, I'm going to keep going. Magnesium nitride formed. Notice this is a combination, so I'm building a compound from its elements. The elemental form of magnesium is just Mg. So then I just need to balance by placing a 3 in front of it. 3 Mg's combines with elemental form of nitrogen, and notice based on charge, magnesium is a +2, nitride a -3, so we crisscrossed and found our formula, and we balanced the equation. Letter B, when sulfur trioxide decomposed, the elemental form of oxygen is what's missing, and it comes as O2. not just O. So then I have to work to balance 2 S's, 2 S's, 6 O's, and 4 plus 2 is 6 O's. Are you getting good at these? Copper must be a +2, bromide a -1. When silver kicks out copper, the elemental form of copper is Cu. The compound is silver, who's a +1, bromide, who's a -1, just AgBr, right? Do not bring subscripts. Find the new subscripts when you are balancing by charge. So I have a copper, Cu, plus AgBr, silver bromide. I'll need to balance 2 groups of Ag plus 1 group of copper 2 bromide yields a copper and 2 silver bromides. And we had one more, a double replacement reaction. Sodium's a +1, hydroxide a -1, H is a +1, bromide a -1. Oh my gosh, these are easy, all +1, -1s. So here we'll have sodium bromide, also a +1, -1, so it's electrically neutral. And then in H, who's a plus, OH is a minus, and so that balances as water. And a double exchange, sodium bromide and hydrogen hydroxide, commonly called water. That takes practice, my friends. Keep going. If you can work more and more and more problems, recognizing the patterns, and especially this skill requires practice, filling in what's missing and then going back to balance. Don't cheat yourself of the opportunity and think that you're proficient until you've worked enough problems. All right, that's my soapbox for the day. When we think about another pattern of change, this pattern of change is known as oxidation and reduction. I'd like to discuss what this means in this lesson as well. So we're looking at the bottom of page 5, oxidation and reduction. Oxidation we are going to define as the loss of electrons. The reduction is the gain of electrons. When something is oxidized, another must be reduced. They occur simultaneously. A redox reaction is what we'll commonly call redox, an oxidation-reduction reaction. It involves a transfer of electrons from one element to another, a redox reaction. Here's a little helpful little sentence, little game I always say. Just like horses need oats for clear brown eyes, I have a little sentence. Leo, the lion, says grrr. Leo the lion says grrr. Here's what that means. The loss of electrons is oxidation. The gain of electrons is reduction. That's a little helpful sentence to let me remember those two definitions. Leo the lion says, grrr, Leo, oh, loss of electrons, oxidation. When you lose electrons, we remember that you become more positive on the number line. And when you gain electrons, you remember that you become more negative on the number line. Gaining electrons makes you more negative. Oxidation, loss of electrons, makes you become more positive on the number line. So wherever we have oxidation, we have reduction. And I put a little example of this type of chemistry where I can see a piece of copper wire bent around kind of like a popsicle or wood splint. And it's just sitting into a solution of silver nitrate. So I'm going to show you what I'm seeing. I have a piece of copper wire, so I'm going to add in just that little S to let you know that it's in the solid phase, a piece of copper wire. And it's reacting with a solution of silver nitrate. And I'm going to put in AQ to let you see that it's a solution. So it's not a solid salt of silver nitrate, which are kind of like gray crystals, but it's dissolved in the water. So copper wire is the solid phase sitting in a solution where I've taken crystals of silver nitrate, stirred it up in water, and made a solution. Can you see what's happening over time? There's an observed equation, observed chemical reaction occurring. Notice that the solution is turning blue, and blue is showing that copper is going into the water. You will learn that a nice blue color is copper in water. And what about what's plating out? What do you see starting to deposit on the wire? What are that solid pieces? Well, that's pure silver element. The element of silver is falling out of solution. Here's what we see. The copper displaced the silver, and silver came out as a solid, and the copper went into solution, forming a positive charge. And now it receives the aqueous sign to let you know it's now dissolved in the water. So when copper reacts with silver nitrate to form silver metal and copper 2 nitrate, we have what's known as a redox reaction. And let's show how that occurs. I'm going to simplify this to alleviate, get rid of the nitrate. And I'm going to tell you that the nitrate is a spectator ion. Now, what does that term mean? It simply means that it didn't change in charge. Notice that the nitrate appeared as NO3 minus 1 on this side, and it appears over here as NO3 minus 1. Since it did not change, it's referred to as a spectator ion, and we can just get rid of it in our equation. And rewriting that in terms of showing solid copper reacted with 2 silver ions in solution to form 2 silver atoms in the solid phase and an aqueous copper ion. We have had a change of charge. And that's our very definition of a redox reaction. Let's investigate. Copper in the elemental form is a charge of 0. Copper is not an ion at all. It starts as an atom, and atoms we know are neutral, no charge. On the right side, it formed an ion, and that ion carried a +2 charge. So the half reaction of copper would show copper as a solid, forming a copper +2 ion, and the loss of 2 electrons. You see how this is electrically balanced? +2 and 2 electrons creates a neutral charge overall. This is an oxidation half reaction. Copper lost 2 electrons to go from 0 to +2 charge, an oxidation half reaction. Copper is being oxidized. It became more positive by loss of electrons. Now let's see what happened to the silver. Notice the silver started with a positive charge. It then gained electrons to form the atom of silver. Gaining electron, notice I'm just keeping the electrons lost equal to the electrons gained. This is known as a reduction half reaction. You would say that silver is reduced, making it say that it becomes more negative on the number line. To go from a plus charge to a 0 on the number line, think of it, if you're at a +1 and you go back to a 0, you're becoming more negative. Copper here on a number line started at 0 and went to a +2. That's becoming more positive. Oxidation becomes more positive. Reduction becomes more negative. And to be a balanced redox equation, the number of electrons lost has to equal the number of electrons gained. So we wrote out all kinds of great information here that showed the two half reactions where copper and silver changed charges. The changing of charge means it's a transfer of electrons, and that's exactly what a redox is. Copper lost 2 electrons and silver gained those electrons in a redox reaction. Now, one more vocabulary word. If copper is oxidized, and it is, it forced silver to be reduced. So it is called the reducing agent. Silver was reduced, and it was, but it forced copper to be oxidized. So it's called the oxidizing agent. All right, lots of good chemistry there. Let's talk through another practice and really kind of get our feet wet with redox. Here's a next practice, and I tried to give a visual as well. Zinc is placed into a solution of copper 2 nitrate. So here's the element zinc, right? This is just an electrode plate. A hunk of zinc is an electrode, a nice thin piece of zinc metal. Elemental zinc starts as a solid. It's placed into a solution of copper 2 nitrate. Now, I'm going to let you know that the nitrate is a spectator ion. That when it appears unchanged on the left and the right, we're allowed to just leave it out of our equation. So since it didn't change charge, we'll just leave it out and just focus on the 2 metals. Zinc started as an element. Elements are in their natural state, so 0 is its charge. Copper started as a +2 ion. I know so because of the Roman numeral. After time goes by, you start to see the zinc change color in solution. The zinc goes into solution, forming an ion. Zinc is a fixed charge. You need to memorize that. A fixed charge of a +2. And the elemental form of copper now with its 0 as its natural state charge. When zinc started as a solid and went to an aqueous ion that carried a charge of +2, it did so by losing 2 electrons. This is the oxidation half reaction. The loss of electrons. Copper started as an aqueous ion and went to an elemental atom. To do that, it had to gain 2 electrons. To become +2 down to 0 is a gaining of electrons, making it become more negative. This is the reduction half reaction. Now we know to be a balanced redox reaction, the number of electrons lost has to be equal to the number of electrons gained, and it is. They're transferring 2 electrons total. Since zinc is being oxidized, it's called the reducing agent. Since copper is being reduced, it is called the oxidizing agent. There is a transfer of 2 electrons between the element zinc and the aqueous ion of copper through this chemical change. So let's put that into some vocabulary. We said zinc went from 0 to +2. The loss of electrons is oxidation. Copper went from a +2 to a 0. The gaining of electrons is reduction. The transfer of electrons is known as a redox reaction. Redox occurs when you have a change of charge. A compound that is oxidized is known as the reducing agent. And so in this example, zinc was oxidized, so therefore it would be called the reducing agent. And since copper was reduced, it is known as the oxidizing agent. The agents are always on the left side of your equation. Just as what is oxidized and what is reduced, they're always reactants. Agents are oxidized and reduced, therefore on the left side. So a compound that is reduced is the oxidizing agent. The compound that is oxidized is known as the reducing agent. I'd like to try some more practices with you for redox. The oxidation and reduction features really just kind of give us an activity series of how many electrons are lost or gained. And so when I wanted to point this slide out, I just wanted you to see that anytime you see oxidation, notice that the electrons are always on the product side. They are being lost. And notice that for reduction, they always occur on the reactant side because they're being gained. And so loss of electrons is oxidation, Leo. The gaining of electrons is reduction, grr. The placement of the electrons on the left side shows reduction. The placement of the electrons on the right side shows oxidation. To be a balanced redox reaction, electrons lost must equal the electrons gained. So here's an example of rusting. Identify the reducing agent and the oxidizing agent. Any element in its natural state, you know that it's not charged. An atom is neutral, so it has an oxidation state of 0, no charge. The elemental form of iron is Fe as a solid, 0 charge. The elemental form of oxygen is O2, so it's not an ion, it's a molecule, so 0 charge. In the compound now, just think about uncrisscrossing. The iron must have been a +3 and the oxide is a -2. Ionic compounds are built of charges. Remember that the metal will be positive. The nonmetal is always negative. Positives are written first, nonmetals are written last, and you just uncrisscross to find out those charges. So you can see that iron went from a 0 to a +3. If 0 to a +3 is oxidized, it's becoming more positive. The iron is now known as the reducing agent. The oxygen went from a 0 to a -2. Becoming more negative is a reduction. Gaining electrons is reduction. So therefore, since oxygen was reduced, it is known as the oxidizing agent. Iron, the reducing agent. Oxygen was the oxidizing agent. That was all we had to do, is recognize the change of charge and find out, based on oxidation and reduction, label out the agents. Oxidation results in the gain of oxygen, the loss of hydrogen, and reduction is the loss of oxygen and the gain of hydrogen. That's a classic example of an organic chemistry model. Let's see what's changed charge here. Here I have an oxygen in the elemental form as a 0, and now over here I can see it's combined as a -2 in the water. Hydrogen stayed the same. Carbon had to be a -4, and it went to a +4. Identify the oxidizing and reducing agent. Oxygen went from a 0 to a -2, and it did so in both places, so it really did become more negative. Becoming more negative is a reduction process, so oxidizing is the oxidizing agent. And friends, if you can label just one of them, you know the other has to be the opposite term. So the methane is your reducing agent, and the oxygen is your oxidizing agent. That's really all we had to figure out. If this change of charge, let's apply this second rule here. Who gained more oxygen? Well, the carbon did. The carbon had no oxygen here, but it has oxygen here. Gaining more oxygen is oxidation, right? And therefore, it's known as the reducing agent. Oxygen was reduced, and therefore we know it is the oxidizing agent. Oxygen gained more hydrogens. That's reduction. Gaining hydrogens is reduction. Identify the species that is oxidized and reduced in each of these reactions. Write out the half reactions to show how many electrons are gained or lost by the species. You have some practice to do on here in the bottom of page 6. I want you to work through those, come back to the video, and we'll check, and that will be the conclusion then of this lesson on balanced chemical equations and the patterns of change. But stop now, practice this out, and then come back when you're ready to check. Okay, so let's come back. I'll just start with letter A. The element zinc reacts with 2 ions of hydrogen to form the zinc plus 2 ion and hydrogen gas. So let's pull out the 2 half reactions. Zinc is starting as a solid and going into the aqueous ion of plus 2. So starting with no charge and going to a plus 2 charge is a loss of electrons. This is oxidation, becoming more positive. The 2 hydrogen ions started as aqueous ions and turned into the elemental form of hydrogen. To go from a plus 2 to a 0 required gaining 2 electrons. I should remember to leave room. So plus 2 electrons. Becoming more negative requires gaining. So this is the reduction half reaction. How many electrons are lost or gained? Well, there's 2. And so in that particular part, we had a transfer of 2 electrons. Zinc lost 2, hydrogen gained 2. And what is being oxidized and reduced also gives you the agents. Since zinc is oxidized, it is the reducing agent. And since hydrogen was reduced, it is the oxidizing agent. Let's try letter B. I'm going to start just by breaking them up into 2 half reactions. Iron started as an aqueous ion of a plus 3 charge, and on the opposite side I can see it became a solid iron. No charge at all. So to do that, it had to gain 3 electrons. That's a reduction half reaction. The other element is aluminum. Started as a solid and went to an aqueous ion of a plus 3 charge. To do that, it lost 3 electrons. We want to keep the charges balanced, so that's an oxidation process. Notice that a plus 3 and 3 negatives combine to give a 0. So that's what I'm doing. I'm balancing the charge. The aqueous ions will always have the electrons with them. So how many electrons were actually transferred? 3. To balance the charges, there was a transfer of 3 electrons. You can see that in your reaction, iron was reduced, so it is the oxidizing agent, and aluminum was oxidized, so it is the reducing agent. Let's look at letter C. I'll break them apart into two halves. 2 iodide ions in aqueous form. Ions are always aqueous. And on the right side, I can see it now in its elemental form of I2. So it became more negative. This had to gain 2 electrons. 2 iodides gains 2 electrons to form a molecule of I2. Remember, the charges always go with the electrons. So this gained electrons, that's GOB, that's a reduction half reaction. The next part of that equation gives us the elemental form of bromine, which is actually a liquid. And then on the opposite side, the aqueous ions, the charges here. You know what? I'm wrong, and I'm glad I caught this because look what I did. These negatives, that's a total of -4, and that does not balance 0. And I just noticed that it made no sense to add electrons to negative ions. Ions on side of the charges, if they're positive only, positive charges, because I need to correct this right away. I'm so sorry. Would you mind erasing with me? Thank you so much. And I'm glad I caught this because it made no sense to have negative ions wanting more electrons. And you probably thought, oh, Hanson, you're going crazy. Let's redo this. 2 iodide go to iodine. This right here balances both sides to be -2. That's the correct balance. Now, both sides have the same charge. That's a balanced equation. This now is oxidation. And the next one was the bromine, the Br2, went to 2 Br negative. Well, that means it had to be 2 electrons on this side to create a balanced charge. They're both -2s. And gaining electrons is the reduction half reaction. Ooh, there. So that's correct now in the notes. The gaining of electrons, oxidation there for iodine, reduction for bromine. All right, so that means the I negative was oxidized, so it's the reducing agent, and bromine was reduced, so it is the oxidizing agent. That was C. I think I'll fit in D, silver bromide. So here, AgBr is now giving us the elemental form of both elements. Bromine is a diatomic molecule, so that's why you see it written as Br2, and then we had to go back and balance. Now, break these apart and keep in mind that silver bromide is an ionic compound built of charges. So to break this into its 2-half reaction, ionic compounds, remember these are charged ions. You have 2 silver plus 1 aqueous ions forming 2 Ag. Now this would require gaining 2 electrons, so there's your reduction half reaction. And the negative ion of bromide goes on to form its element Br2, and to do that it had to lose 2 electrons, and there's your oxidation half reaction. Loss of electrons, oxidation, makes the bromide the reducing agent, and it makes the silver the oxidizing agent. And one more, we had zinc and mercury oxide. Let me get that down here. Zinc plus mercury oxide, and it went on to form zinc oxide and mercury. I want you to notice that the oxide did not change charge. It just stayed as the OXIDE oxide. It's O minus 2, and it didn't change charge. Do you remember that word? That word for something that's in the reaction but did not do anything in terms of changing charge is called a spectator ion. So you can really just get rid of your spectator and rewrite your two equations such as this. The elemental form of zinc as a solid formed the aqueous ion of zinc, which was +2, and to do so had to lose 2 electrons. That's an oxidation process. Now, the mercury started as a +2 charge aqueous ion. It had to gain 2 electrons to form the elemental form of mercury, which is actually a liquid at room temperature. That's your reduction half reaction. If zinc was oxidized, it is the reducing agent. If mercury was reduced, it is the oxidizing agent. Oxidized and reduced are patterns of chemical change that show a transfer of electrons. In this lesson, it was very large. We talked about combinations, decomp, single and double replacements and combustions, and a next broader category called redox reactions. Again, let me emphasize, there are instructional videos that supplement this lesson from other authors. I would encourage you to find more practice, especially with redox, because it tends to be a tripping point for some students who need a little more practice. Go into the next link and find some more practice on redox. That finishes up our lesson. When you come back, it's time to bring your calculator out. We'll be looking at Avogadro's number and the mole in our next lesson.